Question 7. So first of all, in part AI, we need to find the value of P if the block is on the point of toppling about the H through B. We need to complete the force diagram. I've got the friction force and force P at my diagram at the moment. We have to complete it with two more forces. So first of all, it's the weight of the block, which is applied at the center of the block, mg. And secondly, it's the reaction force. And what we know about the reaction force, that if the block is about to topple about HB, the reaction force is acting through B. So that's the position of the reaction force. Now, in order to answer this question, we have to write down the equation for the moments. We know that if the block is about to topple, the total moment of all the forces acting on this block is 0. So if we take moments about point B, see, if we find the moments about point B, we can see that there are two forces which have non-zero moment about B. It's the weight and the pulling force P. The friction force has moment 0 and the reaction force has its moment equal to 0 because their lines of action go through B. Let's write down the moment of the weight. It will be mg multiplied by A. So that's the distance from B, so the perpendicular distance from B to the line of action of the weight. Now, in order to work out the moment provided by force B, let's split this force into horizontal component, which is P cos theta, and the vertical component, which is P sine theta. What's the benefit of doing this? Because once we've done this, you can see that P sine theta doesn't provide any moment at all because its line of action goes through B as well. So the only component of P which provides a clockwise moment is P cos theta. Let's write it down. So 3a is again the perpendicular distance from B to the line of action of P cos theta multiplied by P cos theta. So that's the equation that we needed. A is cancelled, and the expression for P is then mg over 3 cos theta. That's the answer to part I. Now, let's do part II. Part II. For part II, again, let's have a look at the force diagram we have. If the block is about to slide, it means that the force diagram basically remains the same, apart from the fact that R is probably hasn't reached its critical position when it acts through B, and the reaction force acts somewhere here. So this is what we've got for the situation when the block is about to slide. Now, let's write down all the equations we have. If the block is in a limiting equilibrium, we know that the magnitude of the friction force is equals to mu r. What else we can see from the force diagram is the components, the vertical and horizontal components of the forces acting on this block. They are balanced. So let's resolve forces vertically. We have R plus P sine theta equals to the weight mg. And from this equation, we have the expression for R mg minus P sine theta. Now, if we resolve forces horizontally, you can see from the force diagram that the magnitude of the friction force must be equal to P cos theta. Now, let's substitute the expression for the friction force and for the reaction force into the first equation we have written down. And by doing this, we have the following P cos theta equals mu mg minus P sine theta. Okay, let's go to the next page. So P cos theta equals mu mg minus P sine theta. Now I have to rearrange this equation in order to get the expression for P. Let's remove the brackets. We've got mu mg minus mu P sine theta. Let's move this term over to the left hand side and take P as a common factor. We've got cos theta plus mu sine theta equals mu mg. So P equals mu mg over cos theta plus mu sine theta. And that's the value of the force, the minimum value of the force required for the block to slide. Now we're in a position to answer part B of this question. Given that tan theta equals a half, find an equality that mu must satisfy if the block topples before it slides. Let's use this condition then. The block topples before it slides. It means that the force which is required for the block to topple mg, 3 cos theta, is lower in its magnitude than the force required for the block to slide, cos theta plus mu sine theta. So that's the inequality to start with. Now, let's try to simplify it so we can cancel mg and do a bit of cross multiplication because it's safe here. Cos theta plus mu sine theta is always positive because theta is guaranteed to be less than 90 degrees, so cos theta is positive. We can rewrite this inequality in the form cos theta plus mu sine theta less than 3 mu cos theta. Now, if we divide through by cos theta, we've got 1 plus mu tan theta less than 3 mu. Now let's collect like terms for mu. We have 1 is less than mu, 3 minus tan theta. Now, if tan theta equals a half, we can rewrite this in the form 1 equals mu multiplied 3 minus a half, 2 and a half, which is 5 over 2, which means that mu has to be greater than 2 over 5. And that's the end of question 7.